Ukrainian scientists learn from nature how to optimize motion in fluids. Researchers of the Hydromechanics Institute of National Academy of Sciences control airflows using plasma discharges, to raise, in particular, the aerodynamic efficiency of airplanes.
Aerodynamics is one of the most important components of any airplane. We seek to optimize the performance of aircraft by improved aerodynamics design. To that end, extensive work is carried out on numerical simulation and experimental testing of aerodynamic models.
Investigations of aerodynamic processes and characteristics are implemented under the direction of Dr. Nina Yurchenko, head of the Laboratory for Advanced Aerodynamics and Interdisciplinary Research, Associate Fellow of the American Institute of Aeronautics and Astronautics. The researcher who is capable both to generate innovative ideas and to see them through to their practical applications. Gold reserve of Ukraine is the people who make history and can improve the welfare of Ukrainians. Scientific investigations of Nina Yurchenko and her team are multifaceted and groundbreaking. They required a unique experimental facility, and it was built as the central component of a new laboratory.
Our goal is to reduce drag of moving objects or to improve the aerodynamic performance of bodies in a fluid flow. It implies a reduction of fuel consumption and, accordingly, reduced environment pollution.
An airfoil is a basic object of aerodynamic investigations. This shape is what creates lift and enables an airplane to take off. Lift is a component of aerodynamic force perpendicular to the direction of motion. The air that moves more quickly above the curved wing puts less pressure on the upper surface compared to the wing bottom. The higher air pressure pushes the wing upward, producing lift and giving an airplane the power to fly.
Of course, a basic task of aerodynamics design of an aircraft is a choice of an airfoil profile, its geometry. Aerodynamicists are in a continuous search for optimal shapes that will generate the necessary lift at a minimal drag.
The problem of drag reduction has challenged world scientists since the invention of the airplane. Many approaches have been and are being proposed and tested, but true optimization has not been achieved as yet. Scientists of Hydromechanics Institute have suggested significant new concepts to control flows of air, water or other fluids economically and efficiently.
About 40 years ago, I happened to study first marine swimmers, like dolphins and sharks. Their skin structure appeared to be the more regular, the higher speeds the species demonstrated. This adaptation instrument, created by natural evolution, gave rise to the development of drag-reducing techniques based on riblets, tiny longitudinal grooves on the surface.
However, like any passive flow control devices, riblets provide a favorable effect only for a narrow range of flow parameters. Besides, polymer riblet films were proven to be economically inefficient.
Riblet coatings of an aircraft surface have a short lifetime. They must be replaced every 1–2 years, which is pretty expensive. That is why riblets didn't find applications in aircraft designed and produced in Ukraine.
Our investigations are basically focused on active methods, enabling us to switch the flow control function on and off at necessary moments or motion regimes. Now we work with virtual thermal riblets, which in fact are organized thermal wakes downstream of arrays of localized plasma discharges.
Plasma generation is a field far from fluid dynamics. It required involvement of specialists in electrodynamics.
Scientists of Moscow Radiotechnical Institute in Russia. According to our aerodynamic requirements, they developed for us a special device, a generator of the microwave-initiated plasma.
Microwave radiation is a short electromagnetic wave, longer than infrared but shorter than radio waves, used here for remote selective surface heating or for localized generation of plasma discharges.
Numerical modeling provides the basic knowledge of flow physics, while experiments give a quantitative indication of the improved aerodynamic performance.
For various tasks of aeronumerical simulation, we use personal computers as well as the available access to supercomputers, such as the one located at the Moscow State University.
The Lomonosov system is equivalent to 10,890 modern quad-core PCs for computations with the same efficiency. That is, the work done within hours on a Lomonosov system would require a month using just one computer.
Numerical simulation can give us flow patterns depending on a model type and flow parameters. Here, comparing vortex shedding behind two models, we demonstrate that the second one has a better aerodynamically optimized geometry.
Following the numerical recommendations and our experience of many years, models with flow control systems are designed and fabricated for internal testing. Typically in experiments we measure lift, drag, pitching moment, together with pressure distribution over the model surface for various values of flow velocities, model angles of attack and control parameters. Usually we carry out measurements for angles of attack starting at 2 degrees. If we work without float control, the lift, initially growing with growing angles of attack, suddenly drops at 16 degrees. However, our flow control system can increase this critical angle at least up to 18 or 19 degrees.
4 forces act on an airplane: weight, drag, thrust and lift. By reducing drag, we also can reduce thrust. If we are able to increase lift, we equally can increase weight.
Here we can see the generated lift when the flow is controlled using arrays of microwave-initiated plasma discharges. The measurements have proven that the developed strategy of thermal riblets and our tested engineering realizations are feasible and rather effective.
Flow control device. It's based on specifically localized suction blowing of air from a near-surface layer of the model. This task was formulated to simulate a more complicated, multidisciplinary problem based on application of plasma discharges. In particular, my PhD work is focused on a search of flow control parameters, which can result in a most favorable impact on the flow.
Typically, parts of the whole wind tunnel facility are designed in a laboratory and fabricated in a machine building plants. However, we use our lab workshop with available processing machines to adjust or modify certain details. By now, Dr. Yurchenko has received the 4th grant for her projects, is about $1 million.
Such funding seems to be fantastic for many Ukrainian scientists, but it enabled the research team not only to obtain fascinating scientific results, but also to essentially enrich the experimental base of the Ukrainian Academy of Sciences with the unique laboratory for advanced aerodynamics and interdisciplinary research.
I think I will always remember Dr. Yurchenko's presentation on plasma aerodynamics. As a diplomat, I don't have many chances to think about these complicated scientific problems, and just being very impressed by what she was able to create. The US supports Ukrainian scientists like Dr. Yurchenko because this is the way to create a modern Ukraine. The way to do this is through innovation.
Then, what can we learn from Nina Yurchenko's team success?
Together with our laboratory, our team is developing like a living organism, coordination and minimal dead load, only to provide stability in our successive development stages.
Thus, the unique laboratory of Nina Yurchenko can further give jobs to specialists in various fields of science and engineering. Let us wish these enthusiastic people a controlled flow of new ideas, resourcefulness and possibilities to help us live better.